All right, so last time we were talking about solving recurrence relations, linear, homogeneous type. And so let's do one more example of that. Have you guys heard of the Fibonacci sequence? Excellent. All right, so the Fibonacci sequence is a sequence where this actually is come out wrong. It's basically supposed to be an is equal to an minus 1 plus. This should be a plus. So just please be aware of that. I don't know why it looks like a minus, but it's supposed to be a plus. So the nth element of the Fibonacci sequence is equal to the sum of the previous two. So in order to get the third one, we have to have the first two as initial conditions. And there's the A0 is 0 and A1 is 1 initial condition. So what's A2? A2 is going to be 1 plus 0. So A3 will be 1 plus 1. A4. Okay? So the sequence will go like that. Now, if we look at the substitution technique that we use in this linear homogeneous recurrences, we're going to use the same substitution again. A sub n will be r to the n for all n values, right? So what we're going to do is once we substitute, now instead of having a to the n, we have r to the n is equal to r to the n minus 1 plus r to the n minus 2. We again divide by r to the n minus 2 power, and that gives us a constant here, it gives us a linear r here, and it gives us a quadratic r here. When we look at this equation, which is now a quadratic equation, we cannot factor this equation. So the solution to solve, we use, what's the technique we use for quadratic equations when we can't factor it? Quadratic, it's called the quadratic formula, right? Minus b plus or minus the square root of b squared minus 4c all over 2a? 2a. Over 2a? Okay, so we use the quadratic formula. When we use the quadratic formula, we find out that we have some irrational roots. So when we solve it, then r1, the first root becomes 1 plus radical 5 over 2. The second root is r2 is 1 minus radical 5 over 2. So since these are my two values, so all of them are going to work, and the general solution will be alpha times the first root to the n times beta times the second root to the n power. Right? Very strange result, because we have a Fibonacci sequence. We know the numbers are 0, 1, 0, 1, 1, 2, 3, 5, 8, and yet we're getting these radical 5s in there, which looks a little crazy. But that's the general solution. How do we find the actual solution? The specific solution? We need to solve for these initial conditions. So we need to solve for when n is equal to 0. When a is equal to 0, we have a naught is equal to this to 0 is equal to. So therefore it's going to be alpha plus beta. So alpha plus beta will equal to 0. What does that tell you? They're going to be opposites, right? They're going to be opposites. And we also find out that when a1, when n is equal to 1, a1 is 1, so therefore 1 is going to equal to alpha times this to the first power plus beta times this to the first power. Okay, so we can see over here now, so we look at the initial conditions and we basically get this, what I told you before, alpha plus beta is equal to 0. Okay, and we also get alpha times this to the first plus beta times this to the first is equal to 1. We can do a substitution, because if this is true, then alpha is equal to minus beta. So then I go to the second equation and I substitute minus beta for alpha, minus beta for alpha, and now I have an equation that only has beta in it. Once I solve it, I get beta is equal to 1 over the square root of 5. Okay, actually it's negative, right? So therefore, alpha will be opposite of that, will be positive 1 over the radical square root of 5. So now, from my general solution, where alpha and beta are unknown, now we know this is 1 over radical 5, and this is negative 1 over radical 5. So we can put them in an order like this. 1 over radical 5 times this plus, right? 1 minus this times that. So this is our specific solution. This is our specific solution. And then we can actually check this out because it appears to be kind of a crazy solution. Why would that be the Fibonacci sequence? And I can't answer that question except to say, well, it is. That's just, it just happens to be true. So we can try it right there. Notice that if we try for A1, remember what A1 is supposed to be? A1 is supposed to be 1. So we get 1 over radical 5 plus 1 plus radical 5 over 2 to the first power, right? So we're going to get 1 minus this one, and then when we multiply, notice that it's going to be 1 over radical 5 times 1 plus radical 5 minus 1 plus radical 5. Okay? So what do we have? We have 2 radical 5 on the bottom, and this cancels with this, and we get 2 radical 5 on the top, and that's equal to 1. So it's just incredible. Now, so you might try it just to convince yourself. For example, so we have 0, 1, 1, 2, 3. So try putting a value of 5. See what you get. Of course, that takes a lot of work. So you're probably not going to try it, but this is the correct result. So the Fibonacci sequence is a recursive or a recurrence relation, but it has a closed form. And it's very, very important. Okay? So this is example number 3. I'm not going to do it because you can do it on your own, right? The same stuff. Again, we're going to use the same idea. We're always going to be doing this by substituting a sub n is equal to r to the n. That's our only tool that we have. It's a linear homogeneous recurrence relation. That's the only tool we're going to use, okay? All right, so we're going to do that. Now, so this is, the previous examples we're talking about recurrences, and recurrences are good ways of solving what kind of algorithms? What kind of algorithms are naturally mapping to mathematical recurrences? Recursive algorithms, right? Where t of 0 or t of 1 are our base cases, right? And t of n are our general cases that bring us back. Remember, every recursive algorithm, the idea of the recursion algorithm is that some big problem comes in, and we solve it by doing a little piece of it, and then recursively solving the remainder of the problem. And then recursively solving the remainder and the remainder. So what's going on in the problem size for each recursion? It's getting reduced. And we're reducing it so that it eventually reaches the base case. Once it reaches the base case, then we then go back, and everything is resolving at the top level finally, right? As it's returning. So recursive algorithms very well work with recurrences, recursions, that type of stuff. But then we have other algorithms which are iterative algorithms. So iterative algorithms are algorithms that do not have a recursion, but they have a loop. Now, I hate to tell you this, but sometimes recursive algorithms have loops too. They have recursions and loops. Sometimes we loop our recursions. That's another whole story, right? For example, remember I asked you a problem last time? So, remember we said what kind of a problem would have a sub n is equal to 6 sub a minus 1 plus 5 times n minus 2, a minus 2? Well, basically what you would do is you would have the n comes in, and then you loop 6 times, putting in n minus 1, and then loop 5 times, putting in, so you could do it that way. So that's what would happen. So if you have iteration around the recursion, it's still recursion. But if you have iteration with no recursion, then you just have iteration. So there's a different approach we're going to take, and the approach to take for iterative algorithms, which are loops, are essentially to count the number of iterations they take. Sometimes if it's an outer loop only, we just count this one, but if we have 2 loops that are nested inside each other, we have to look at this one and this one. Sometimes we may have 3, etc. So those types of algorithms lend themselves naturally to being solved mathematically by summations. So a summation is basically just the sigma, right? So we simply count for all the number of values from the low index to the high index. Okay, so let's look at an example. So let's say we have a binary tree. So a BST stands specifically for binary search tree, And what that means, and we're going to look at those types of cases, is that this is the root of the binary search tree, and then anything to the left of it would be keys that are smaller values. And anything to the right would be bigger values. So if you're looking for something, for example, in a search tree, and you want something smaller than this, you go here. But if you're looking for something bigger than this, then you go here. If it's a match, you're done. But if you're looking for something bigger, here. If this is not a match, you're done. Because there's nothing smaller than this, nothing bigger than this, you're done. Okay? So you either match it or you don't match it. But that's a binary search tree. My question is, what is the average depth? Now we'll talk about what that means of a BST node. So this is a tree, and this tree is made up of nodes. Let me define those nodes. So this is the root. This is another node, These are other nodes. All of these nodes are referred to as internal nodes. Every node that contains values in it is an internal node. So what is an external node? An external node is, if you look over here, there could be a child here, but there isn't. So the pointer is null. There also could be a child here, but there isn't. So that pointer is null. So anything that's a null pointer, you can think of it as referencing an external node. I might have mentioned that before. So external nodes are nodes that are not containing keys, and they are effectively the null pointers. So if you look at this tree, how many internal nodes do you see?
6.
Internal nodes. 15. Right? Because all of them are internal nodes. But how many external nodes? 16. 16, because basically these are the only ones that have any null pointers. And 1, 2, 3, 4, 5, 6, 7, 8, 10, 12, 14, 16. So the external nodes are the nodes that are effectively the null pointers. Notice that this pointer is not null, neither is this. No, 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 no. Yes, 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 16 times. So 15 internal nodes here, 16 external nodes. All right? What if I had the following tree? So I have a root, I have a right child, I have a right child. How many internal nodes?
2.
I have a root, I have a right child, I have another right child. How many internal nodes? 3. How many external nodes?
2 external.
Missing this, missing these two. 4. Okay. Now I have 1 left child, right child. How many internal nodes? 3. How many external nodes?
4.
Okay. I'm not saying wrong. I'm saying yeah. You're right. So 4 external nodes. So both of the. So what if I have boom, boom, boom? How many internal nodes?
3.
How many external nodes?
4.
Is it possible to have? Is it 4? 4 is correct. Is it possible to have 3 internal nodes and not 4 external nodes?
No.
So now I can see that the gears inside your brains are moving. They're like, tick, 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 tick. You're thinking, I don't know the answer, but it's interesting. I'd like to know the answer. How do I find the answer? How do I find the answer? Well, imagine this. If you have a tree that has 0 internal nodes, what's that mean?
No.
There are no nodes. So how many external nodes are there? You can consider 1 because you have a null pointer. If you have 1 node which is internal, how many external do you have?
2
2. Is there any other choice?
No.
Okay, so if I add a second internal, I'm basically having 1 external here, I'm adding 2. So 2 goes to 3 here. How about these 2? Also goes to 3. So it looks like if you have 2 internal nodes on a BST, you have to have 3 external nodes. Okay. So this is not a proof, but it's something to think about. We might want to prove it. How could we prove it? We have to think about that. All right. This is not the problem we're working on right now, but it's something to think about. We'll come back to these ideas. Okay. So first, we need to set up a model. We want to find out what is the average depth. Now, when we talk about the depth of a node, we're talking specifically about, so if you look at the depth is essentially how many steps how many edges away from the root. So if you are the root, how many edges from the root? 0. You are the root, so you are 0 away. So therefore the depth of the root is 0. The depth of the children of the root, both of these guys are 1,
1,
2, and 3. So to find out the average depth of a node, what we would do is basically say, well, the average means you're going to add up all their depths and then divide it by the number of nodes. Well, the number of nodes is 15, so the average depth here would be 0 plus 2, right?
3,
Plus
3,
8 plus
16.
24? This is 0, 1, 2, 3, so this would be 24, right? So it would be 3 times 8, 2 times 4, 1 times 2, right? 0 times 1 times 0. So what you would do is you add up that number and you divide it by the number of nodes, which is 15. That's your average depth. So what we're going to do is to make our job a little bit easier, we'll limit our value of n, which is the number of nodes, to 2 to the k minus 1. And the reason for that is because when a tree is full, and this is a full tree, one where every level that exists is maximally filled, every level has a maximum number of nodes if it exists. Notice it has 8, 4, 2, 1. You cannot have any more. If you had 1 here, to make it full, you'd have to add 16 nodes. Then that would also be full. So full trees can have 1 or 3 nodes or 7 nodes or 15 nodes or 31 nodes or 63 nodes. All of these are 2 to the k minus 1. So to make things a little bit easier, let's limit ourselves to 2 to the k minus 1, which is approximately equal to 2 to the k. It's only off by 1, so it's not a big deal. So given, for example, that n is equal to 16 and k is equal to 4, n is the number of nodes and k is the height of the tree. And the height of the tree is determined by the longest path from the root to any external node. Well, the external nodes are here, they're invisible ones, right? So therefore from here we're going to go 1, 2, 3, 4. That's the external node. So actually, to get to any of these external nodes here, they're all 4 because the tree is full, so all the paths are quite similar, right? They have the same height. So the height of this tree is the maximum such path, so it's going to be 1, 2, 3, 4. Height of the tree is 4. Okay. So we can set up a model that looks like this. So one way, now if I ask you to do this, nobody is immediately going to say, okay, I know exactly what it is, I'll just set up a summation. What you want to do is you always want to look at a small example and model it. So for example, I have 1 node with a depth of 0, 2 nodes of a depth of 1, 4 nodes of a depth of 2, and 8 nodes of a depth of 3. The depth is 0, 1, 2, 3. The depth is increasing linearly. But the number of nodes goes 1, 2, 4, 8. The next one is 16. The number of nodes is increasing exponentially. So we have a product of a linear increasing variable, which is the depth, times an exponential variable, which is the number of nodes. But that's how we're going to sum all of the depths. The number of nodes given a depth, plus the number of nodes given this depth, plus the number of nodes given this depth, add them all up. So we're going to have a summation of products. And that will look like this. So here you can see what I have here. 0. Now here is, I just have a little simplification here. Actually, I don't even like this approach number 1, so I'm going to skip it, because it's not the best one. We'll look at approach number 2. Approach number 2 is even better than this one. It's more clear. So what we have is 0 is the depth, 1 is the depth, 2 is the depth, 3 is the depth. Now, and then how many nodes are at depth 0? Well, 2 to the 0, which is 1, which is very nice. So we have 0, 2 to the 0, plus we have 2 nodes of a depth of 1. Those are the children of the root. We have 4 nodes, a depth of 2. Those are the grandchildren of the root. And then we have 8 nodes with a depth of 3. Those are the great-grandchildren of the root, if you will, right? So once I see this pattern, then I'm going to try to write this in terms of a summation. Because I want to generally solve the problem, not just for this tree, but for any tree that looks like this one. So I will sum, and I'm going to see that the depths are going 0, 1, 2, 3. The height is 4. But the depths are going 0, 1, 2, 3, so I might go instead of from 1 to 4, where height would be k, I'm going to go 0 to k minus 1. which is 1 less than the height. Okay? And then I'm going to multiply that by 2 to the I. So when I is 0, I have 0, 2 to the 0. This is this one. When I is 1, I have 1 times 2 to the 1. When an I finally goes up to 3, I is 3. This is going to be 3 times 2 to the 3, which is 3 times 8, which is 24. So we know that the summation from I to k of I2 to the I is k minus 1 times 2 to the k plus 1 plus 2. Now the proof of this is, we're going to go over this, but it's an important result. This comes up a lot, so we want to make sure that we can solve this summation. This summation is not a trivial summation. I don't actually expect you to know it until the midterm, then you'll definitely know it, and for the homework, because it's important for us to know this when it comes up a lot. So we're going to find out why this is the case. But actually, it is the case. So that means if I to the k, I to the I is equal to this, then I can, so if this is a known result, I can substitute this value into the equation above, and I can then go from 1 to k minus 1, I to the 2, or the I, and then since k here is k minus 1, this becomes k minus 1 minus 1 is k minus 2, and this becomes k minus 1 plus 1, which is k, and plus 2 is plus 2. So I substitute, because again, this k value is arbitrary. So if it's equal to k, that's what it looks like. But if k is equal to k minus 1, then it adjusts. Easy enough, right? So, now what is k? Well, k actually is the log base 2 of n minus 1. If you look at our tree, notice that the number of nodes in this tree is 15. 15 plus 1 is 16, and the log base 2 of 16 is 4, which is also the height of the tree. So if I have a full tree, I'm not proving it, but I'm just saying it, if I have a full tree, then the height of that tree is going to be log 2 of n plus 1. Lg of n plus 1. That will be the height. So what I have here is, since k is log 2 of n plus 1, this is nothing more than log 2 of n plus 1 minus 2. And this is 2 to the power of log 2 of n plus 1, which is n plus 1, which we did when we looked at logs, but we're going to look at those again too. So that's going to be, so this is going to be this plus 2. Now, the average depth of the node is going to be therefore all of this divided by the number of nodes. So that is our result. Okay? Now what exactly is that? Well, basically it's, so this is log 2 of n plus 1, but that's very close to log of n. Right? Okay? Minus 2, so it's about log of n. And then we're multiplying it by very close to n. So this is very close to log of n. And this is very close to n. So this is like n log n plus 2. But plus 2 is like, who cares? When n is big, 2 is small by comparison. So this is really like n log n over n. So it kind of looks like it's going to be close to what?
Log n.
Close to log n. Okay. For large values of n, this is going to tend to go close to log n. And if you look at it, so you look at the values of k. No, so when k is equal to 4, the average depth is 2.27. And the reason it's 2.27 is because when I add up 0 plus 1 plus 1 plus 2 plus 2 plus 2 plus 2 plus 8 times 3, and I divide them by 15, it comes out to 2.27. Depth 0, 1, 2, 2.27 is someplace in here. Because that's 3, that's 2. So 2.27 is a little bit lower than 2, but not 3. So when I do this, when k is equal to, for example, 16, notice that the average depth is 14. When the k is equal to, when the depth of a full tree is 10, 1023 nodes, then the average depth is 8. Now, let me ask you a question. Let's consider 10, 1023, and 8.01, which is effectively 8. How much better is this, or how much less deep is this than the maximum depth of this tree?
0.19.
How much is it? What's the difference?
1.9. 1.9. 1.9.
So the answer is about 1. Because if a tree has depth of 10, remember the root is 0, so the deepest level is 9, but the average is 8. Now you might, so this is one of these crazy situations. So you got a tree, again, focus only on the 10 line right now. So what you have is, you have a tree that has a height of 10. Height of 10, so you got 1, 2, 4, 8, 16, 32, 64, 256, 5, 12. That's it. That's it. 512 is the bottom level. And that tree has a maximum depth of 9, but the average depth comes in at right around 8. Now you say, why is the average so low? Well, the reason the average is so low is because 50% of the nodes are at 9. 50% of the nodes are at 9. Would you agree with that?
Yeah.
Roughly 50%, right? So 512 are in here. So how many nodes are above the 512? From 511, right? Because when we go 1, 2, 3, it's 3 nodes. And then when we add it, we have 4. 4, and then we have 3 here. So we have 1, 2, 4. Now that makes 7. And then if I add this level, that makes 8. So the bottom level always has 1 more than everything else above it for a full tree. So therefore, in a tree of 1,023 nodes, 512 of them, about half of them, are at the very bottom level. What part of them are at the next level up? Approximately? What percentage? About a quarter of them, right? Half at this, a quarter at this, an eighth at this, and 16 at this, 132nd, 164. So very few of them are not very deep. Most of them, in fact, we'll say about 75% of them are at maximum or maximum -1 depth for any full tree. For any full tree. If a tree has a meg of nodes, 2 to the 20th, -1. So we're going to have half a million of them are going to be at the bottom level, 250,000 are going to be at the second lowest level. You can see why that's going to pull that average depth down. So we are not surprised at this because we understand that the deeper you go, the more frequent that is. So the probability of a deep node, so if you're looking for a node, and you're looking for a node in a tree that has a height of 10, and it's a full binary search tree, if each node is equally likely, what's the probability that you're searching for a node that's at the deepest level? 50%. It's the same 50%. I just asked it in a different way. And 75% of the time, you're going to be searching for a node at the bottom 2 levels of depth. So 50%, 75%, what if we add 1 more level? What does that bring us up to? So we're going to have 1/2, 1/4, 1/8. So it's going to be 4 eighths. How many eighths? You have 4 eighths, 2 eighths, 1/8. What's that? 7 eighths. So what percentage of the nodes is 7 eighths? That's 100% minus 1/8. Minus 1/8 is 0.12, 0.125, right? That's 12.5%. So it's 87.5, almost 88%. So about 88% of the nodes, 80% of the nodes are going to be at the bottom level. So if you're searching with equally likely for any node in the tree, 88% of the time you're going to hit the bottom level or the next 2 levels. 88% of the time. And out of that time, you're most often going to go more often than not at the very bottom level. Okay? Just want you to think like that. Okay. Let's take a look at the binary search. So the binary search, let's see if I have the code. So the binary search, we're going to look at an iterative approach for the number of search in a binary search approach. So basically, the probability of comparisons What is the probability that we'll only have one comparison? Well, the probability that we'll have one comparison is the probability that we match right away. The probability of two comparisons is that we'll fail to match on the first one, but we'll match on the second one. So we're going to have 1 over 2 to the k minus 1. Again, we're going to use n is equal to 2 to the k minus 1. So that's 1 out of those, which is 2 to the 0 over 2 to the k minus 1. Make sense? Okay. The probability of two comparisons is going to be 2 over 2 to the k minus 1, which is 2 to the 1 over 2 to the k minus 1. And the probability generally of k comparisons is going to be 2 to the k minus 1 over this whole set of n, which is 2 to the k minus 1. So what we're going to do is we're going to now try to solve this as a summation. So we're going to say, therefore, assuming the element is in the array, the average number of comparisons is going to be the summation of all possible numbers of comparisons of the number of comparisons times the probability of that number of comparisons. So that's going to be, that's the number of comparisons is I, and that's the number of the general comparisons. As I is increasing, right? Does that make sense? So we have to solve this summation. So solving the numerator, we can write this as I times 2 to the I minus 1. This is just the numerator, I times 2 to the I minus 1. Later, we'll add the denominator. But let's solve this top first. Okay? So to solve the top, we're going to have I times 2 to the I minus 1. But I times 2 to the I minus 1, we can rewrite 2 to the I minus 1 as 2 to the I minus 2 to the I minus 1. What that means is that 2 to a lesser power is equal to 2 to 1 greater minus the lesser power. For example, 2 to the 7th is equal to 2 to the 8th minus 2 to the 7th. And the reason that's true is because 2 to the 8th is 2 times 2 to the 7th. 2 times 2 to the 7th is 2 to the 8th. So if you take 2 to the 8th and you subtract 2 to the 7th, you have 2 to the 7th left. So that's why if you have this 2 to the I minus 1, if you go to the 2 to the I, 1 higher, and subtract 2 to the I minus 1, you have it. Now you might say, well, why are we doing that? Well, I'm going to show you that in more detail later on, but the bottom line is we're trying to solve this summation. Okay, this summation. This summation is not exactly the same summation as we had before. Before we had the summation from 1 to k, I, 2 to the I. This is I, 2 to the I minus 1. So it's a little bit different summation, so therefore the result cannot be used. We cannot use the previous result. Remember the previous result? N minus 1 times 2 to the k plus 1 plus 2. Someplace we had it. Where was it? Did it just go by it? No, it just went by. Okay? So this is k minus 2 times 2 to the k plus 2. That's this summation. It's close to the one we're doing, but the one we're doing right now is we have I times 2 to the I minus 1. So the solution is not applicable here because we can't have I and 2 to the I minus 1 because then the two i's are not the same. So that problem has to be solved a little bit differently. So we're going to solve it differently here, and I'm going to go through how to do that. The bottom line is we're going to come out with a solution of k minus 1 times 2 to the k plus 1. Notice it's very close. How close is it? The other one was what?
K.
The other one was k plus 2. So basically this is minus 3 to the k. The difference. And now when we have that result, we can then stick that result over 2 to the k minus 1, which is our denominator that we kind of ignored for a little bit of time. And so that would be the result. And of course, each value of k is log of n plus 1, log 2 of n plus 1. So now we substitute for that. So we have log of n plus 1 minus 1 times 2 to the k, which is n plus 1, plus 1 over n minus 1, which is, again, 2 to the k minus 1. As we simplify this further and further, you can kind of see we're getting n log n minus n. Well, if this is minus n, it's like log n times n minus n, so log n minus 1 times n. But that n is not going to be that significant, and then we're going to dividing it by n, so those n's will kind of cancel, so we're expecting the answer to be kind of logarithmic, mostly, right? The order of magnitude is going to be logarithmic. It's going to have a little bit of stuff in there, but it's not going to be linear, it's going to be definitely logarithmic of something. So the average number of comparisons, assuming the element is an array, comes out to this. Now, as n goes to infinity, what does that mean? As n gets larger and larger and larger, what happens? Then n plus 1 over n approach what? Approach 1. Because if n is getting larger, for example, 5 over 4, that's 1.25. But 11 over 10 is 1.1. A million over 999,999, 1.0. So it's approaching 1. So this is approaching 1. This is just LG of n plus 1. Okay, so we have LG of n plus 1 minus 1. So this is what we call the large n solution. Large n, so when n is large, basically these things just is a function of 1, and so we just have LG of n plus 1 minus 1. So it's basically, and what's LG of n plus 1? That's k. That's the height of the tree. So it's the height of the tree minus 1. Well, isn't that what we got for the average anyway, right? This is the large n solution. So you can see that that's what we end up getting. Okay? So binary search, very similar results here, very, very similar result we have here. Okay, any questions? Any questions? I mean, really, if you have any questions about any of the things I talked about, if it's not clear, I would love to answer it if you have anything. Anybody? Before we go on. Nothing here, nothing here, nothing here, nothing here. Again, this stuff, I will go through this one on the next set of slides, exactly how I want you to do this, because you need to be able to do that, but that's not, don't ask me about that, because we're going to do it. Okay, so let's go to the next sequence, which is some of the mathematical stuff that we want to do. All right, so let's talk about some of the mathematics that we're going to be using, and we're going to be using a bunch of different things. So these are some of the common things that we're going to be using. Sometimes we have the functions that are like a floor function or ceiling function. This is a floor function. So this shows you the floor of 2.992, because it's called the, this is actually the smallest integer greater than or equal to, less than or equal, sorry, the greatest integer less than or equal to 2.99. And if you go in the number line, if this is 2 and 2.99 and you stop at 2.99 before 3, the greatest integer you passed was 2. If you're at -5 and you're approaching -4 but you don't quite make it, the largest integer you crossed was -5. So you always go back to the left on the number line to get the floor. If you are at an integer, at 2, then you're okay, you stay. So the floor function is the integer if it's an integer, but if it's not an integer, we want the greatest integer less than or equal to that number. And the greatest integer less than or equal to 2.01 is 2. And it's 2. Now the ceiling function is going to be the smallest integer, which is greater than or equal to what we have. So 2.99 is going to be 3, 2.01 is going to go up to 3, and integer will stay as an integer. Okay? All right, we have logarithms. Logarithms are going to be extremely common for us. So in general, the natural base logarithm is ln, natural log of x. So y is natural log of x. The graph of that looks like this. So it's basically increasing, but then the rate of increase is always slowing down, always slowing down, always slowing down, but it's always increasing, but slowing down. Now, if we take the derivative of the natural log function of x, the derivative of natural log of x, it's going to be 1 over x. The derivative. Remember what the derivative is? The derivative is the slope of the tangent line. So for example, if you look at this, what value is this? This value is like 10, tick, 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 right here. So if I draw a tangent line here, the derivative of this tangent line at x is equal to 10, the slope should be what? According to this derivative. 1 over 10. 1 over 10, or 1/10, right? How about at 2? That's going to be more like 1/2, right? Notice this is not drawn to scale. Because you see the scale is very large units, these are very small units. But that's what it is. So you understand, so the derivative of the tangent line to a curve at a particular value, so the derivative of natural log is 1 over x. Well, the integral is basically the inverse function of the derivative. So if we take the integral of 1 over x, we're going to go back to natural log of x. Natural log of x. And the integral it can be interpreted as the area under the curve. So basically, if you have the integral of 1 over x dx, if you give it a starting value of 1 to 2, then that will be the area under the curve 1 over x, from 1 over 1 to 1 over 2 on the y-axis. What does the function look like, 1 over x? What does that look like? So 1 over 1 would be what? 1. And 1 over 2? 1/2. And 1/4. So it would start to approach what value for large values of x? Would approach 0. How about for very small values of x, like 1/2, 1/4, 1/8, 1/16? It's going to go to infinity. Okay. Good. Okay. So that's the function. So logarithms. All right. So when we have logarithms, and logarithms do come up a lot in our complexities. So these are increasing functions, as you know, and they are strictly increasing, and they are what we call one-to-one functions. One-to-one functions are functions that never two values of x have the same y. So for example, if you have a parabola looks like this, right? So that means if you freeze it, tick, 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 these two different x values have the same x. The sine function, many x values have the same value, so it's not a one-to-one function. And it's not an increasing function. Increasing means it's always increasing. So increasing could look like this. Always increasing could look like this. Okay? Or even could look like this. But it's always increasing. Like the logarithm increases, but it starts increasing less and less, but always increasing. It's never the same. So it's a one-to-one function. Okay. So log of any base is strictly increasing. If x1 is greater than x2, then log of any base of x1 is greater than log base of x2. That's always true for all our log functions. Log b is a one-to-one function if you cannot have the log of x1 and x2 of the same base be equal to each other. That means that you cannot have a horizontal line cross 2 points on the function. That makes it a one-to-one function. By definition, the log of any base of 1 is 0, because the log is always base to what power is equal to 1. Well, I don't care what the base is, 2, 3, 4, 5, e to the 0 power is equal to 1. So that's why. And then log base b of b to the a is just equal to a, because log base b of b to the a is what power do I raise b to make a? And the answer is, I raise b to the a power. So therefore the log of base b of b to the a is a. Log base 2 of 2 to the n, 2 to what power is 2 to the n? Nth power. Okay? Log base 2 of 2 to the n, if we have a log of an exponential expression, then the exponent can come out also in front of the log as a factor. So log base 2 of 2 to the n is just n times log base 2 of 2. Well, log base 2 of 2 is 2. What power is 2? 1. So log base 2 of 2 is 1 times n is n. The product of logs is the sum of each of the log factors. So log base 2 of 8 times 16 is log 2 of 8 plus the log 2 of 16. That's 7. If you don't believe me, what's 8 times 16? That's 2 to the 3rd times 2 to the 4th, which is 2 to the 7th. Log base 2 of 2 to the 7th is 7. And the log of a quotient, okay, is going to be the difference of the numerator minus the log of the denominator. So the log of 1024 over 8 is the log 2 of 1024 minus the log 2 of 8. And that's 7. If you don't believe me, that's 2 to the 10th, and this is 2 to the 3rd. 2 to the 10th divided by 2 to the 3rd is 2 to the 7th. Log 2 of 2 to the 7th? 7. Okay, any questions about that? So these are called, so some of these, this is called the product rule. Product rule, this is called the quotient rule. Okay, this is the power rule. So the power rule is log base b of x to the a. So again, if we take a log of an exponential expression, the power of the exponential expression can come out in front of the log. So therefore, it's going to be equal to a times log b of x. So log base 4 of x to the third is nothing more than 3 times log base 4 of x. And log base 4 of 64 to the third is 3 times log 4 of 64. And what power do you raise 4 to make 64? 3. 4 to the third power. 4 times 4 is 16, times 4 is 64. So that's going to be 3. 3 times 3 is 9. And this is a change base rule. So if you have a log of one base of x, you can say that's the same as the log to another base of the same x. But you have to divide it by the log of the new base of the old base. So for example, here we're trying to convert base 10 to base 2. So the old base is 10, the new base is 2. So log 1024 is log 2 of 1024 divided by log base 2 of the old base. So you can see that these values are the same. So these two logs are only differing by a what? By a constant. Constant. And the constant is log 2 of 10. Same thing here. Log 2 of 1024 is equal to log base 3 of 1024 divided by log base 3 of the old base. That's called the change base rule. And the last example I'm going to use for these logs is if we have a to the log b of x, we can exchange the x and the a and write it as x to the log b of a. So notice the log b stays, and here the x and the a are exchanged and they're equal. And the reason they're equal is if you try to solve this problem, you could solve it by taking the log base b of both sides. So imagine you take log base b of the left side, you get log b of the left side equals log base b of the right side. Right? So now you have log base b of a to the log bx. Log base b, x to the log ba. But these are now exponential expressions, which means that log bx is an exponent which can come out in front. So you get log b x times log b x times log bx times log ba. And here, this comes out as a factor too. So we have log ba times log bx. And if you look at them, they're the same expressions. So that shows you why we can interchange the parameter of the log and the base. So if we're exponentiating a log, we can switch the parameter of the log with the base. And we'll do that in some examples that we're going to work on. Okay, let's talk about summations, because we're going to be doing a lot of summations, recursions, all that kind of good, fun stuff. So this first example you can show this quite easily, that this is the sum as I goes from 1 to n of I. Basically, it is the summation of the first n positive integers. So it's going to be 1 plus 2 plus 3 all the way until we stop at n. Now this one can be shown quite easily, and I can show you how you can do it without doing a lot of math, but the next ones are not so easy. So if you have 1 plus 2, rather 1 and then 2 and 3 and 4 and 5 and 6 and 7, 8, and then go to some number, let's say you go to 99. So 1 plus 2, so the summation as I goes from 1 to 99 of I, how much is that? Well, that tells you that it's going to be equal to 99 times 100 over 2. Well, 100 over 2 is 50, so it's 50 times 99. Whatever that is, right? What's 10 times 99? 990. So 5 times 990. Do the math. Okay. You don't have to do it out loud, just do the math. All right, so now if you wanted to find out, if you weren't sure how to get this, you could say, well, if I add the first number to the last number, when the numbers are going from 1 to 99, 1 plus 99 is how much? 100. And if I take 2, and the previous one, it's 2 plus 98, that's 100. 3 plus 97, 100. So they're all going to add up to 100. Well, so we are creating from a set of numbers, we're creating pairs. And each pair is basically the sum of the first number plus the last number How many pairs do we have? Well, the number of pairs in n numbers is n over 2. So therefore, what we're going to have is we're going to have right here. Do you see how this is arrived? Do you see how we arrived at that? It's kind of, it's kind of intuitive. So each of the values is going to be n plus, each of the pairs is n plus 1, right? Like 1 through 99. 99 is n, so 1 plus 99 is 100, that's n plus 1. That's sum of each pair is n plus 1, and the number of pairs is the number of numbers divided by 2. And so that works very nicely. When we get to this one, it no longer works very nicely. Because now we want the sum of the first n squares. What if I wanted the sum of the first n cubes? Not as nice. Not as nice. But the result for that particular summation is 2n cubed plus 3n squared plus n over 6. That's a well-known result. That's a result I'm going to show you how to do, because you need to know how to do it. And the next one is 2 to the I being summed from I equal to 0 to k. So it's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, all the way to 2 to the k. What's the value of the first term?
1.
Second term?
2.
Third term?
4.
4. So what's the next one?
8.
Okay, what's happening with each term? It's being
Adding.
doubled, right? It's being doubled. It's being doubled. So that's a special situation called a geometric series. And a geometric series is a series in which each term is being multiplied by a constant to get to the next term. That constant ratio is 2. But what if this was 3 to the I? Then the first number would be what? If this was 3 to the I, then what would be the first term? 1. And then 3. And then
9.
27.
okay, so what would the ratio be there? The ratio would be 3. And also what would happen if instead of 2 it was 1/2? What would the first term be?
1.
1. 1/2.
1 by 4.
1/4, 1/8, 1/16. Okay, so that also would be a geometric series. So any constant I substitute for 2 would create a different geometric series. Geometric series have a relatively easy solution. We're going to talk about them in general, how to solve them, but the general solution for this one is going to be 2 to the k plus 1 minus 1, but that's not the solution if 2 was 1/2 or 1/3 or 1/4 or 3.8. Okay, that's not the solution. Solution is only for 2. So we need to find out solutions for any case. Okay, and this one we saw already, right? This one we saw already. So we have the summation of I 2 to the I, and you can see it goes from 1 to k. Now what happened if I change the lower index I equals 0 to k? How would that affect the result? Would that increase it or decrease it? It's a trick question. It wouldn't affect it at all, because if I was equal to 0, then the first term was 0 times 2 to the 0, and that would be 0. So actually, we can write that this is I goes from 0 to k, or 1 to k. It's the same in this case. It's not the same here. Because here, if I change this to 1, then what would happen? Then I would be what? I would be taking away 1. So that would, the result would be what? Minus 2. Okay, so it's very, very, so we have to be very careful in doing that kind of stuff. Okay, so what we want to do is let's look at solving this problem in a non-trivial way, so that when we solve more difficult problems, we can apply the same technique. And the technique is going to look something like this. So we want to solve this summation for the general solution, which is 1 to n, the summation of I. So the first n integers. We already know what the solution should be. Let's see if we can do this. So what we're going to do is we are going to actually start by doing the summation of the first n squares. And that equals the summation of I plus 1 squared, where I plus 1 is going from 1 to n. Let's make sure this is correct. So basically, would you agree that this first term is 1 squared, 2 squared, 3 squared, all the way to n squared? Right? Okay, so that's what's on the left side. Let's make sure the right side has the same thing. So the first value, notice that I plus 1, which is the inside here, I plus 1 goes to 1. Well, when I plus 1 is 1, then this is 1 squared. When I plus 1 is 2, it's 2 squared. When I plus 1 is n, it's n squared, so it's the same. So those two are the same right now. I just wrote them a little bit differently. Now what I'm going to do is I'm going to do two changes here. I'm going to take I plus 1 squared, I'm going to actually multiply these to get I squared plus 2I plus 1. I'm going to keep the parentheses on, right? And the second thing I'm going to do is I'm actually going to do something here. I am going to subtract 1 from the index. So I'm subtracting 1 here. So I minus 1 goes to I, n goes to n minus 1, and 1 goes to 0. So I subtracted 1 from the index. Now let's make sure that's still correct. So notice that this is exactly the same as this, right? So I can still use this because it's the same. So what's the lowest value of I? So the lowest value of I is 0, and when I is 0, what's this? 1 squared, which is the same as the first term. What's the last value of I? N minus 1. So that means n minus 1 plus 1 is n, and squared, that's the same as this last value. So they're the same. So I did two things. Number one, I changed the index, okay? And I also multiplied out this binomial squared. Okay, so I have this squared is equal to this squared. Well, basically, the summation of 3 terms is the sum of 3 summations. So what I'm going to have is I'm going to have this is equal to this is equal to, and then what I'm going to do is I am going to bring this one on this side, creating a 0 on the other side. So I'm going to be this minus this is equal to this. So this is the minus I squared from 1 to n on the right side. And this over here is just this, right? So now the summation of 3 terms is 3 summations. So what I'm going to do is I'm going to say the summation of this plus this plus this, summation of this, plus the summation of that, plus the summation of that. So what I have is the summation from 0 to n minus 1 of I squared, plus the summation from 0 to n minus 1 of 2i, plus the summation from 0 to n minus 1 of 1, minus this, equal to 0. Everybody with me? Set up this 0 situation. Now what I'm going to do is I'm going to switch around these summations inside, because I'm noticing that what I have is I have some I squares here, and here, and I'm subtracting some I squares here. That's my goal, is to subtract a lot of these I squares, because I'm not really interested in I squares. I just use them to get a difference for minusing. So what I'm doing is I'm putting this one here, I'm putting this one here, and I'm putting this one here, minus this one. So what I'm seeing here is that what I have is I have 0 to n minus 1 of this minus 1 to n of this. These are the same, but the indexes are different. So what I'm noticing is that on the left one, which is right here, when I is equal to 0, the value of this is 0. So therefore, I can change this to 1 to n minus 1 without making a difference. So that 0 is irrelevant, doesn't count. Now, when I is n minus 1, this is n minus 1 squared, but this also has an n minus 1 squared that I'm subtracting. So the only thing, after I combine all these summations, is I'm going to get only one term for this one, which is going to be the opposite of n squared. And that's why I'm crossing, and n squared stays. Make sense? Okay, and the rest of these guys is going to be the summation of 2i. This is a summation of 1 going from 0 to n minus 1. It's 1 plus 1 plus 1 plus 1 plus 1. How many times am I adding 1? N times. From 0 to n minus 1 is n times. So that's just n. This is the 0 squared, which is nothing, right? So I have summation of 2i plus n plus 0 minus n squared is equal to 0. So I'm really interested in the summation of 2i. So what I'm going to do is I'm going to say summation of 2i plus n minus n squared is equal to 0. Then I'm going to bring these terms on the other side, and I'm going to get a summation of 2i. Now, when I have the summation of 2i, I can just say that's just nothing more than 2 times the summation of i. Because that constant is multiplying every term, so just do the terms and then multiply everything by 2, since you're multiplying everything by 2. So do that, and then, so I will now get the summation from 0 to n minus 1 of I is going to equal to n times n minus 1 over 2. Divided by 2. Okay. So now, and I don't have the answer yet, because what that gives me is the summation from 0 to n minus 1. So what I'm going to do is I'm going to replace n minus 1, or n, by n plus 1. If it's n plus 1, it's going to be n plus 1 minus 1. That will make it n. Changing it here, okay, which is equal to this, because that doesn't add anything to the sum, which is equal to, change this one, this is going to be n plus 1 times n plus 1 minus 1, which is n by 2. Get it? So that's a solution for that one. So that's how do we calculate the sum. Now, when we create, when we did this creation here, I plus 1, what we ended up doing is we ended up having an I squared summation on this side and an I squared summation on this side. When we brought them to the same side, we had a positive I squared summation on the right, and then we had a negative I squared summation on the right also, and that created the canceling of the terms. This is called a telescope. So when you have a telescope or a telescoping series, basically you end up lining two series up and canceling almost all the terms. So that's why we did. So we're gonna use the telescope in another case also. So for this case, I want to show you this case. This is now solving the summation of I squared. Well, we're going to use the same idea. This time it gets a little more complex, because what I'm going to do is I'm going to get the cubes here and the cubes here, and then I'm going to bring this one over here to subtract them. They're going to, again, telescope out most of the terms. So what happens here, this is more complicated, because now when you have I plus 1 cubed, you get these 4 terms. So you're going to get 4 summations. Again, I start with I plus 1 as the index, and then what I do is I subtract, subtract, subtract. When I do that, I balance everything out. And so I have this is equal to this. So now I have this minus that is equal to 0. So now I have these 4 summations minus this one that I brought over here. I rearrange them. So I put, basically do this, 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 and I bring this one here because I'm setting up a telescope for the cubes. Notice that when I is equal to 0, this term is 0, and everything else cancels except for when I is equal to n, and that gives me n cubed. And that's the same thing as before. And so you see what I have? I have this summation. Then I have 3 times 0 to n minus 1, which I already have from the previous result, so I can solve that directly. And so I end up getting this is equal to 0. Then I have 3 times this is equal to 0, because remember the 3 can come out in front of the summation. And once it comes out, I basically am putting this everything as a common factor of 2, and I multiply it by 1/3, and that's what puts a 6 in the denominator. It's the 2 multiplied by the 1/3 on the bottom, makes it a 6. And that gives me the result. And again, what I'm going to do is I'm going to replace, my result says from 0 to n minus 1. I want to go from 1 to n. I'm recognizing the fact that I can already go 1 for n because the 0 adds nothing. So I can say this is 1 to n minus 1. Replace n by n plus 1. That gives me n plus 1 minus 1. And then I get all these nice results here. So it's going to be n plus 1 cubed, n plus 1 squared, plus n plus 1 over 6. This does not look very pretty, so I have to multiply everything out and simplify everything back up again, because I want to leave it in simplified terms. So that's going to give me, basically, when I simplify all of this, I'm going to get 2n cubed plus 3n squared plus n over 6. A little bit of algebra. That's an important result. So that's the sum of the first set of first n squared integers, positive integers. So as an example, let's say you want to add the square I squared for I going from 1 to 4. So you're going to get 1. What's the next term? 4. Not 8. 9. And 16. 16 plus 9 is what? 25. Plus 4.
29.
Plus 1.
30.
30. 30. So what's the value of n?
4.
4. So what's 4 cubed? 64. 128. So 128, remember that, this is 4 squared, 16, 48. So what's 128? Was it 128?
Yeah.
128 plus
40.
176.
plus
Plus
4?
4.
180.
180.
Divide by 6. Does that match? Yes? 16 plus 9 plus 4 plus 1. Is that a proof? No. Could you prove it? Yes. Because you guys are expert and you love proofs. Right? Conrad told me you guys love proofs. You want more proofs. Okay, so this following sequence, this is the geometric series. The geometric series is a series where we have a ratio between terms. Okay? Now, so when we had the summation from 0 to k of 2 to the I, that's what it looks like here, and the solution for this, I'm not going to go through the solution in the class, it's not very difficult, but the solution in the class, the solution that we have for the geometric series is going to be a minus ar to the n over 1 minus r, where a is always the first term of the sequence. Always, a is the first term. R is the ratio of the sequence, so each term has to be multiplied by the ratio to get the next term. If it doesn't, it's not a geometric series. And finally, n is the number of terms that we have, number of terms. So we need a, r, and n. If we have a, r, and n, we can figure out the sum of any geometric progression. Okay? So for example, let's take an example here. So let's say that this one we're going to take is, let's say we want to. Let's say we want to have the summation as I goes, let's say, from 1 to 6. Okay. And let's say we want to have 1 over, let's say 1/2 to the I. So first of all, we have to determine it's a geometric series. So what's the first term going to be? Let's go from 0 to 5 instead of 1 to 6. So what's the first term going to be?
1.
1 plus plus
1 by 8.
plus
1 by 16. 16.
any more?
Yeah. 1 by 32.
Okay. Quickly, add them up. I know, you don't like it there. Okay, so now, A is equal to what? First term is equal to 1. The ratio is equal to, is it a geometric series?
Yeah.
Half of this is 1/2. Half of this is 1/4. Half of this. Okay, so that's a geometric series. What if I had this one? 1/2, 1/3, 1/4, 1/5. Is it a geometric series or no?
No.
No, because what? Because there's not the ratio, right?
The ratio.
They're getting smaller, but they're getting less small. It's not the constant ratio. Okay, so that isn't. So the ratio here is what? What's the ratio? From here to here, I have to multiply this one by
Half.
1/2. And what's the number of terms n? Number of terms is 1, 2, 3, 4, 5, 6. 6. So the solution is going to be, it's going to be equal to a, which is going to be 1 minus 1 times the
6.
ratio, which is what?
Half times 6.
Which is 1/2 to the power of
6.
6 over 1 minus
1/2.
the ratio. So 1/2 to the 6th power is going to be what? 1/64, right? So it's going to be 63 over 64 divided by 1 minus 1/2, which is 1/2. Which is like multiplying it by 2, so it's going to be 126 over 64. Is that what you got in your head? Well, basically everything is going to, and that could be, of course, what, 63 over 32, right?
32.
So how many 32s do you have here? 1. How many 32s do you have here? 2. How many do you have here? 4.
8.
8.
16.
16. And how many 32s do you have? 32. So 32, that's going to be 48, 56, 60, 62, 63. See, it's not so hard. I know. Okay, so that works. So now, the geometric series, so it's easy to figure out what the geometric series, but make sure it's a geometric series. Some series will fool you. I think it's a geometric series, but I'm not sure. I'm going to assume it's a geometric series and take my chance on getting a low grade in the class. That's a bad student. A good student says, It looks like a geometric series, but I'm going to make sure I'm going to write out, what's the ratio? Oh, the ratio is 2. But for the next one, the ratio is 3. Not a geometric series. So geometric series, you cannot have a changing ratio. Once you have the ratio from term 1 to 2, it's got to be the same ratio from 2 to 3, 3 to 4, etc., etc., etc. Okay, so you can see over here, if you have the summation of this sequence, you would get 3 plus 9 plus 27 plus 81, which would be this one, and that would be, and then that would be the same thing as, notice here, the first, what's the value of A? A is equal to 3, the ratio is 3, and N is 4, so it's going to be A minus A times ratio to the N, 1 minus 3. And of course that's going to be equal to 3 minus 3 to the 5th times negative 2, and I'm going to take 3 minus 3 to the 5th over 2, negative 2, and I'm going to multiply top and bottom by negative 1, and I'm going to get a positive difference here and a positive denominator. So it switches these two, switches that one, and that's just going to be 3 to the 5th, whatever it is, minus 3, and it's going to give you 120. Okay? So that's the geometric series. Okay. Now the last one, which is super, super important, is this is the I2 to the I version, because we have to know how to solve this one. This is a very important one. It comes up a lot. And this one is, again, solved by the use of a telescope. So we're going to create a telescope. So we want the summation of I2 to the I, as I ranges from 1 to k. So what we do is we set up the telescope. And the telescope, basically, we recognize that 2 to the I power, as I mentioned to you before, is nothing more than 2 to the 1 higher power minus 2 to the I power. And what that's going to do, it's going to produce from one product, it's going to be the summation of this minus the summation of that. The minus is the key, because now when you have the I to the I plus 1 minus I to the I, you have a difference, and that's going to be helping our telescope. We'll have to do a little bit of work to get the telescope to work. So that's how we start from here, we go to here, and then we multiply. This is the summation of a product is going to be, but it's a summation of this minus this, so it's going to be the summation of this product minus the summation of that product. Now once I write them as a difference of summations, things are not so good. And the reason things are not so good is because now I have I to the I plus 1, and here is I to the I. They're different. They're close, but they're different. So what we have to do we have to modify so they look exactly the same. Exactly the same. So this one I'm going to keep exactly the same. But this one, what I'm going to do is I'm going to lower the index and lower the index. I'm just going to lower the index by 1. But if I lower the index by 1, it's a different summation. So I have to increase the use of the index inside the summation. So if I decrease k to k minus 1 and 1 to 0, then I will increase the use of I from I to I plus 1 and from I to I plus 1. So what I have now is, notice that this is closer now. This is a better match. The good news is the 2i plus 1 is a better match. The bad news is I now have another product. Okay, that's the price. Okay, so now what we have to do is we have this summation minus, and I will have two summations here. So it's going to be this one again, minus I times 2i plus 1, minus summation of 2i plus 1. So now the good news is that the first two summations produce a beautiful telescope. Because now we have the same terms being subtracted. The only difference is we have 1 here, we have 1 here. We have k, we don't have k. So this is only extra term. And the other extra term is when I is equal to 0. Notice the 0 term is 0 anyway. So the only thing remaining from these two summations is what? It's just going to be when I is equal to k, and it's going to be k times 2 to the k plus 1. So this is the only thing that remains from these two summations. And of course everything here disappears. And this is 0, that disappears. So the only thing we left here is 0 to k minus 1 of this. But that is nothing more than a geometric series. What's the first term? No. The first term of this one is 2, because when I is 0, this is 2 to the 1. So 2 to the 1 is 2. The next one is, when I is equal to 1, 4. So 2, 4, 8, blah, 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 blah. So the ratio is equal to 2, A is equal to 2, and the number of terms is equal to what? K. K. Why K? Because 1 to K minus 1 is K minus 1, but that 0 adds an extra 1, so that's K. So that's the geometric series. So let's solve that geometric series real quick here on the side. See if we can solve it, just to make sure that you understand how it works. Somebody left me a very messy board again. I'm going to have to be very mad at the professor. Okay, so let's see. So we have this one. So what's the first term? What's A? A is equal to? 2. Ratio is equal to? 2. Number of terms is equal to?
K.
K. So it's going to be A minus A times R to the N over 1 minus R. I'm going to multiply this by minus 1 over minus 1, and that's going to be 2 to the K plus 1 minus 2 over 2 minus 1, which is 1. So it's 2 to the K minus 1 minus 2. Easy, right? So that geometric series is very easy. Okay, so what we have, so this is 2 to the K minus 1 minus 2. And that's the minus part. So this is 0, this is the full telescope. Cancel, cancel. This is the remaining term. So we're going to get this one minus this one. So K times 2 to the K plus 1 minus 2 to the K plus 1. So it's this minus 1 of those, so it's K minus 1 times 2 to the K plus 1 minus minus plus 2. That's the result. So it's an important result for us because it comes up a lot. It comes up a lot. Okay? Now, in some cases, we're going to find out that K, our K value is going to be log of n, or log of n plus 1. In that case, it's going to be log n times what's 2 to the power of log 2 of n. It's going to be n. So this will be n, this will be log n, and log n. If K is the log of n, then this will be essentially very close to n log n. Okay? So I will give you some nice homework. Today is what, Wednesday? So I think we'll make the homework due on, you have the hours for the students to visit you and talk to you. Homework, I'm almost ready with the homework, so I think it'll come out. Well, actually, it's going to be Wednesday, right? So Thursday. Maybe I'll give you guys until 1 week. So it'll be due before class on Wednesday. Homework number 2, okay? And then we'll go over it next Wednesday.